Waves, refraction, and reflection. Waves transfer energy and momentum from one place to another. There are two types of waves, longitudinal and transverse. Particles in a longitudinal wave move parallel to the direction of wave propagation. So the wave is traveling to the right, and the hand here making the wave is moving forwards and backwards in the same parallel direction as the wave direction. The hand moves forwards and backwards, creating areas of compression and expansion, also known as rarefaction, in the spring. Each ring of the slinky, so here's like a metal piece right here, is moving forwards and backwards in the same dimension as the direction of wave propagation. Here's a very cool animation showing that the wave is moving to the right, but each individual particle is just moving to the right and then to the left and then to the right and to the left. Sound waves are longitudinal waves. Particles of air are pushed by the vibrations of a speaker. The sound wave propagates through space because air molecules are pushing on each other. Individual particles have no net movement. Like one particle is not going to go all the way across the room. They move back and forth due to the compression and rarefaction from the speaker. However, the wave moves to the right. Particles in a transverse wave move perpendicular to the direction of wave propagation. As shown above, the wave is traveling to the right. However, each section of the slinky, so like one little piece here, is moving up and down, as shown by the red arrows. And the person's hand to create this wave is moving up and down, even though the wave is traveling to the right. They are perpendicular to each other. Light waves are transverse waves. All waves have certain attributes. Shown below, we have the wavelength, crests, and troughs marked on the wave. Wavelength, also represented by Greek symbol lambda, is the distance between two wave crests or two compressions in a longitudinal wave. It's also the distance between any two repeating points on the wave that are moving in the same direction. So from trough to trough, that's also the wavelength. From this random point to that random point, that is also the wavelength. The amplitude is the height of the wave, measured from the x-axis up to a crest or from the x-axis down to a trough. The full height of the wave from crest to trough is 2 times the amplitude. So the amplitude is just from here to here. The period, capital T, is the amount of time that it takes for one wavelength to pass by one spot. So if this wave is moving to the right, you could see how long it takes for a crest to pass by this point, and then for the next crest to pass by. So the amount of time between crests passing one point. The frequency is the inverse of period, and is the number of waves that pass by per second. Frequency and wavelength are inversely related. Wavelength is inversely proportional to frequency. So high frequency means there's a lot of waves passing by per second, means they have a short wavelength, right? They're closer together. Low frequency wave has a long wavelength. If you include the speed of the wave, this turns it into an equation. So here's our wave equation. Wavelength equals velocity over frequency. When light, also known as electromagnetic radiation, travels through a vacuum, it has a speed of approximately 3 × 10⁸ meters per second. That's about 671 million miles per hour, or 186,000 miles per second. Sound waves cannot travel through a vacuum, since they are mechanical waves. Mechanical waves require a medium to travel through, like air particles, slinky segments, water, metal, etc. Sound travels through different materials at different speeds. While it travels through air at 343 meters per second, it travels through water at 1,500 meters per second, and it travels through steel at 5,100 meters per second. Calculate the wavelength of light in a vacuum that has a frequency of 4.29 times 10 to the 14th hertz. Hertz is the unit of frequency, and it is 1 over seconds. All right, so we can use our wave equation, which is on the AP Physics 2 equation sheet. Now, what is the wave speed? Well, since we're in a vacuum, the speed of light is equal to c, the constant, 3 times 10 to the 8th meters per second. This constant is also on the AP Physics 2 equation sheet. So we have 3 times 10 to the 8th meters per second divided by 4.29 times 10 to the 14th hertz, and these are 1 over seconds, so you can think of it like this. So these seconds are going to cancel out with those seconds, leaving us with meters. And it's 10 to the 8th minus 14, so that gives us 10 to the negative 7 meters. And 10 to the negative 9th meters is nanometers, so if you move your decimal over, you get 700 nanometers. The light of this wavelength in a vacuum is dark red light. The color of light is not dictated by its wavelength, but by its frequency. When light enters a different medium, here we have light going through air and then into jello and then back into air, it moves slower. The wave speed decreases. The wave moves slower and the wavelength decreases. However, the frequency and therefore the color of the light stays constant. When this happens, light can refract or bend, shown here. So see, this is red light all the way through. The color and the frequency of the light have not changed, but the wave speed changed, which causes the light to bend. Let's examine this further on the next slide. Shown below, the light wave here hits an interface, so this is called an interface, where the light travels at a slower speed, in a slower medium. Since the wave is entering at an angle, the bottom of the wave hits the slow medium first. That portion of the wave begins to travel more slowly than the top of the light ray. So see how this is one wave here, one crest? So this part of that wave crest is now traveling slower than this part of the wave crest, and that causes the whole ray to bend to the right. This phenomenon is called refraction. If a light ray goes straight into a different medium, parallel to the normal, instead of on an angle, no refraction occurs. This is shown here in the green circle. So here is the interface, and the light is going straight in, which means all of the parts of the ray are hitting the new medium at the same time. Different parts of the light ray need to hit the new medium at different times in order for the ray to bend. So remember, if you have an interface like this and the light is going straight in, then all of that light ray is slowing down at the same exact time. Whereas if you're coming in at an angle, then the bottom of that light ray is going to slow down before the top part, causing the light to bend. The ratio between the speed of light in a vacuum, also known as c, and the speed of light in a specific medium is called the index of refraction, also known as lowercase m. This equation is on the AP Physics 2 equation sheet. Water has an index of refraction of 1.33, while diamond is 2.42. The images below show how light bends when it travels from one media to another, for example, from air into water or from water into air. Here is a picture of a stick in an empty glass. Here is a picture of that same stick, but now there's water in the glass. And this image is the first two images superimposed on top of one another, showing that the image is no longer in the same location as the original object. Another behavior of light is reflection. Light originating from point P, here, is incident on the vertical surface M, a mirror, and reflects with the same angle as the incident angle. This is just like the behavior of a particle bouncing off a wall. We will be solving refraction and reflection problems in the next unit, geometric optics. A prism refracts white light twice, at the front and back edges. Unless the light were coming in at this angle, see 90 degrees to the interface, then it wouldn't refract at all. But as long as there is the normal line in an angle of incidence that is not straight into the interface, then it will have a refraction. The color separation observed is called dispersion. The index of refraction varies with color of light. Newton explained this by saying that light particles of different colors travel in a transparent medium at different speeds, thus have different indices of refraction. In general, purple light travels through transparent materials more slowly than red light. So as n varies, so does the deflection from the normal line to the surface. Think of it this way. Purple is going to refract the most because as the white light hits this interface here, it's going to bend the most since it's going fast and into slow, and it travels the slowest inside the glass as opposed to red. That's why it bends the most. Wave theory provides a clearer relationship. As wavelength increases, so the light gets redder, the refractive index decreases. The index of refraction of a material varies somewhat with the wavelength of the light. Each color has a different wavelength. Since red light moves faster through transparent materials, it bends or refracts the least when crossing into a new medium. Violet light refracts the most. The graph shows how the refractive index varies with different wavelengths and types of glass. Dispersion also accounts for the way we see rainbows, with the droplets of water in the air acting as prisms.